Okay, let's start. This is the second part of this session. I remind you that my name is Pavel, and this session is about generators as implemented with C++ coroutines. I have some slides to catch up. We stopped at this slide. And here I told that, in fact, in order to extract values from generators, we need kind of three operations or three facilities, so to speak. We need to check if there are more values that we can extract from the generator. We need some means to get values from the generator, and we need something to in order to advance to the next value. And all of these operations can be represented by the concept of iterators and ranges. And in this case, by having some iterator, for example, from begin call, we can check if there are more values by comparing to end iterator. We can get value from a range, or from, in this case, generator by dereferencing the iterator. And we can advance to the next value, or we can try to advance to the next value by incrementing the iterator. So let's see how it is implemented. First, here an example of how it can be used. At the top, you can see kind of manual use of iterators. So we have iterator I that we got from the begin call. We can dereference it, and after that we can increment it and again dereference it. Or we can just straightforwardly use range 4, which does everything for us, and we just get references to items that that we get from the generator. So here is the things that we have to change in order to implement this interface. We have to change a little bit the promise type. We have to implement iterator type. We have to add begin and end member functions to get iterators. So let's start with promise type. This part is exactly the same as before. It is not changed. Here I done some refactoring, some lighter refactoring, extracted some functions and defined isValue initialized function for our convenience that will be useful later. Otherwise, the behavior is not changed. So let's see at the refactoring, isValue initialized checks if we have any type of result. For example, if we have a value that is yielded, or we have an exception, we consider that we have some initialized value. And this is equivalent to the state being not monostate, so not empty state. We check that our result is not empty, basically. Next is get value. Here we get rid of the check for exception and throw an exception. We extracted it into a different function. Here we just check what kind of result we have and return a reference to that object, either stored inside of our promise type in the result field, or the object that is referred to by the pointer that is stored in the result field. The next one is has exception. That is not changed. We check if our result has an exception stored, and the next function is throw if exception, which checks if we have an exception as a result and rethrows the stored exception. So kind of not much changed. The next one is iterator. This is the overview of our iterator type that will implement. We have some boilerplate. We have constructors. We have comparison operators. We have, of course, increment and dereference. And in the private section, we have a pointer to coroutine handle. So let's start from the beginning. This is the boring boilerplate. We have to define all these types, including the difference type, which kind of doesn't make sense for input iterators. By the way, this iterator is an input iterator. So the next one, the next two, I'd say that are constructors, the default constructor that basically constructs a sentinel iterator that will use as an end iterator. And the other constructor is for construction of an iterator that is connected or refers to some kind of coroutine. The next is the next comparison operators. I, for illustration purposes, define both of them, but you don't have to actually define not equals, because since C++20 not equals operator is synthesized from equals operator, but for illustration purposes, I defined them both. The next one is increment. Here with asserts, I kind of documented that we only can increment our iterator if it refers to a coroutine. So the coroutine pointer, coroutine handle pointer is not null, and the coroutine must not be finished. So basically, it means that this iterator is not equals is not equal to end iterator. So next, when we increment, we resume the coroutine. Next, after the control gets back from the resumption, we check if the coroutine is done. If the coroutine is done, we set the pointer that is stored inside the iterator to null, and we save the initial value into our template intermediate variable. So at this point, after this statement, this iterator basically becomes equal to end. After that, we using the stored pointer, we check if our coroutine that is currently done has an exception. If it has an exception, this function throws the exception. And for this reason, because the coroutine is this point is finished, but we want to have access to the stored exception that possibly the exception that is possibly thrown and stored. We want our coroutine to suspend at final suspend point, and in this case, when the coroutine is suspended at final suspend point for whatever reason, for example, the coroutine finished execution, or an exception was thrown inside the coroutine basically finishes, gets to final suspend point. We ask the coroutine to be suspended. At this point, the coroutine gets into the state that's basically finished. In this case, done, that we can call on the coroutine handle, tells us that the coroutine is done, is in this finished state. And since all the resources are preserved, we can access the promise inside the coroutine handle, coroutine frame. And we can ask to check if there was an exception and throw an exception. So after all of this, we return the iterator, the incremented iterator that can be that can become equal to end iterator, in fact. And the consequence of this is that apart from iterators being input iterators, so probably don't do this considering that these are input iterators. If we use a copy of an iterator to get to the end, to increment and to get to the end, the iterator that we used, in this case I, becomes equal to end. But we didn't touch k iterator, and after the coroutine is finished, k becomes invalid. So I, after the loop, I becomes equal to end, but we did not touch k iterator, and k at this point is invalid. So we have a question: should you not check for the presence of an exception in get value? No, we'll get to that. We don't have to check. These were the. Let me get back. Yes, these were just pieces that we'll use later to get the behavior that we want. This is for our convenience, for functions defined for our convenience. So yes, sorry, let me get back. Yes, so probably don't do this for input iterators, and in this particular case, don't do this either because the saved copy of an iterator becomes invalid after the generator finishes its execution. So the other operation that we need to define for iterators is dereference. Here again, we assert that this iterator must be connected to a coroutine, so the coroutine pointer must not be null. The coroutine must not be done. That is, we must be at the point of immediately after we yielded a value from our generator, and we return by reference the reference that we get from get value. In this case, you can see that this operation and the previous operation, the previous operation, this operation, incrementation, is not no except, so it can throw exception, as you can see inside the if clause. And here, the dereference operation is no except, so the dereference operation does not throw exceptions, and that's why inside the get value, we did not check for exception. We did it earlier during incrementation. So now we defined promise type, we changed promise type, we defined iterator. Next, we need to define begin and end operations. And in the begin function, which is not no except, so begin can throw exceptions. First of all, we check if the coroutine is done. If the coroutine is done, is indeed done, we return just an iterator, indicating that when you compare begin to end, that the generator has no more values. The next is constructing an instance of iterator, providing a coroutine handle that is connected to this generator. We check if a value is initialized. So basically it says that if we are at initial suspend point, then we need to resume the coroutine, so we get to a co-yield, or the coroutine can be finished, and at that point the iterator becomes equal to end. So since we already defined all of these in the iterator implementation, we just call the increment in this case, and after that we return it. I implemented it like this because I want to call begin multiple times. For example, in this case, I want to check begin and end, and if begin iterator equals end iterator means that we have no values inside the generator, and we can, for example, return from this function or do something else. Otherwise, we get to the range 4, which also calls begin the second time in this case. And at this point, we can iterate over the values if we have any values. So this is kind of important. It will be important a little bit later. And so in the begin, we, after doing the check and increment, in case we need to, we return the instance of the iterator. The end function is very simple. We just return default constructed iterator, which is basically a sentinel iterator, and it contains null pointer to coroutine, indicating that it is not connected, and therefore this is a sentinel end iterator. So these are the changes that we had to make. Notice again that begin can throw and never throws. And here's an example of how we can use this interface. So this is our coroutine that may throw, for example, and this is an example of how we can use it. In this case, we just use range 4 to iterate over elements of elements that the generator can return to us that are yielded inside the generator. And let's go over how it might work. So when we from outside use the range 4 to iterate over values, we get to the we get inside the coroutine. Let's suppose we successfully got values. We start to loop over values and yield each value. So in this case, when we first ask for a value from the generator, we resume the generator, get inside the generator, yield the next value, then go back, use that yielded value, then go back, yield another value, back and forth. And eventually we run out of values, in which case we exit the loop. We implicitly execute coroutine. Coroutine calls return void, which kind of does nothing. We go to final suspend. Final suspend tells us to suspend the coroutine. And after suspending the coroutine, the control returns back to outside code, and we exit this outside loop. This is kind of the mental model that you can have to reason about this code, this example. Let's now consider if something throws an exception inside the coroutine. So as before, when we ask the generator for a value, using in this case range 4 loop, eventually we get an exception thrown inside the function body. Unhandled exception is called on the promise type. After that, we go immediately to final suspend. Final suspend tells us that we need to suspend the coroutine at final suspend point. After that, the control gets back to the outside code, and either the begin that we called, or incrementation operation on the iterator that we called rethrows the stored exception. So for the purpose of being able to rethrow the stored exception, we need to suspend at final suspend point. So the resources and promise type in which we store the result, including the exception, is alive, and we can have access to that, and we are able to rethrow that exception in this case. So at this point, you know almost everything you need to know about how generators work, for real this time. And this was supposed to be the end of the previous slot, and we can get to all the stuff that I wanted to present to you. So let's remind ourselves. Here's our generator, example generator. Here is how we can use it when to manually, explicitly write a for loop. In this case, begin and incrementation may throw in case an exception is thrown inside the generator. And the reference never throws, because if begin throws or incrementation throws, it means that there is no no reason to expect that there is a value, and we can't dereference an iterator in the state that the generator has no values. I hope it makes sense. So other option is kind of lazy iterators. In this case, incrementation does not throw, it is no except, but dereference throws instead. So, and also we can have has exception function, which tells us that without throwing an exception, that in the current state the generator has an exception, or rather iterator that is connected to the generator has an exception. And all we need to do is to replace iterator with lazy iterator. Everything else stays the same. I will not show you the implementation of lazy iterator. You can find it in the bonus section of the slides that will be available later. So in this case, in the case of lazy iterator, begin and end do not throw. Instead, the reference throws. And here, neither begin nor end nor incrementation throw. We can, if we want to check if iterator that points to the generator has an exception. For example, if we don't want to handle it, we can just break out of the loop and leave the generator in the exceptional state. It will be okay. Resources will be freed correctly if everything is managed by RAIA style wrappers, for example. And otherwise, we can just, if we have no exceptions, we can dereference the iterator, or we can just get rid of the check and dereference the iterator, and the dereference operation would throw if we had an exception. So this is the consequence of that is that if we, in the state that the iterator has an exception, every time we dereference that iterator, it throws an exception, but it's just kind of peculiar detail consequence of this kind of an implementation. So the next part is yielding values from nested generators, because why not? We can have generators, we can use generators inside other generators, and we would like to yield values that we get, for example, from inner generators outside this current generator. So in this case, here is our old friend bar generator. We have now a bus generator that yields some values before iterating over values that we can get from bar generator. And why not? We can go deeper. Here we have a Cook's generator, which creates a bus generator. Oops, I'm sorry. And we want to get the first value from the bus generator to change it a little bit. For example, in this case, we multiply it by 33. Then we yield the result. Then we increment the iterator. And after that, we don't care to modify other values that the generator can have, and just yield all the rest values from the generator bus. So in this configuration, we have the outermost generator, and we have two nested generators, and in total we have to do up to 3 resumes and suspends when we want to yield just one value. This is inefficient, and as you know, we want that our implementation to follow zero overhead principle, and for that we have recursive generators. So using recursive generators, we can write the code like this. In this case, we don't have to iterate over values of a nested generator. We can just yield the whole generator, and in the outermost case, here we have a generator bus, the nested generator bus. We yield one modified value, and after that we yield the whole rest of the values that the generator can have. So we basically just yield the generator. So yes, I forgot that I animated this. So I will not show you the implementation of recursive generator because we have no time, unfortunately, for this to go over the implementation. But I will try to show you some graphs, some schematics that hopefully will give you an idea of how nested generators work. So here we call cooks to get the to get our outermost generator. At this point, a coroutine frame for cooks is created. Inside of coroutine frame, we have a promise. And inside of that promise, we have a result, and we have 2 additional fields that signify the root, the kind of reference to the root generator and the reference to the continuation. These fields are needed to track nestedness. I will show you how they come into play. So after we created our generator, we want to iterate over its values. So we go inside the generator, we resume the generator. Inside of it, we create another generator. For it, a coroutine frame is created, in this case, bus. Then we want to get a value from that generator. So we go inside of that generator, we resume the coroutine, we yield one value. From bus generator, we get back to our outermost cooks generator. We get that the yielded value from dereferencing the iterator. We multiply it, yield the result, and get back to the outermost code, outermost loop. So now we want to get the next value. We resume the cooks generator. It gets to the last statement in this case, where we yield the whole rest of the bus generator. And at this point, we set the root of the bus as our outermost generator cooks, and we set continuation of cooks to the generator of bus, to the coroutine frame of bus. So in this configuration, when we try to get the next value from cooks, we know that it has a continuation, and instead of resuming and suspending all the stack of the coroutines, we can go directly to bus and get a value from bus coroutine directly, bus generated directly. In this case, we go straight to inside of bus. We resume the coroutine. We immediately yield a value and suspend bus coroutine, and we get back to the outermost loop. When we ask for the next value, we get straight to bus, because we so here we iterate over cooks values, but since we set the continuation for cooks as non-empty, we get straight to bus. In this case, we yield next value. After we return, after asking for the next value, we get here. Here we construct a new generator, in this case bar. Coroutine frame for this generator is constructed. We have to set the root to our outermost cooks generator, and we have to reset our continuation from bus to bar. So the next value that we ask will be from the bar generator. So we ask some more values. We get to bar generator. We exhaust all the values. At this point, we get back to bus generator. Bar generator served its purpose. We want to destroy it. The destructor is called. Before that, we reset the continuation to bus. After that, to clean up bar instance, we call the destructor is called, and at the end of the scope, and the coroutine frame for bar is destroyed. So after that, we get back to our cooks outermost generator, and similar thing repeats. We reset the continuation. We after that the control flows of the body. The destructor for variable g is called, and the bus coroutine frame is destroyed and frees all the resources. So after that, we get back to our outermost code, our outermost loop, and we have no more values in our cooks generator and loops. We exit the loop. And in this presentation, generator and recursive generators are different, because for recursive generator, we need some additional fields, which is overhead, though a reasonably small one, but zero overhead abstraction and whatnot. So we have a question: why not set bus continuation to bar instead of the cooks continuation? Let me go back. Probably here. Why not set the bus continuation to bar instead of the cooks continuation? Yes, I get it. So the point is that we ask for values from cooks generator, and if we set it like this, so we would have to imagine that you have an arrow of from bus continuation to bar. In this case, this is not better than just yielding values that you get from immediately the next level. So you would have to resume and suspend around like 2, in this case, generators instead of 1. And because we ask for values only from Cook's generator, we with this kind of shortcut, we can not care. We can how do you say it? We can get straight to the current continuation. We don't have to consider any number of generators that may be in the stack. So there may be 10 generators in the stack, and we don't have to go every step through all the 10 generators. We can go straight to the currently active generator. So that's why we change the reference, the continuation reference to concrete leaf generator instead of having a kind of linked list of continuations. I hope I answered this question. So yeah, overhead. Okay, so we have STD generator proposal that is, to my knowledge, accepted into C++23. It works very much like recursive generator, but probably will be implemented more efficiently than what I showed in the slides. This is its specification. Again, it probably should be no discard because it doesn't make sense to call the coroutine generator function and not use the generator that it returns. We at least need to store the resulting generator into a variable, and it is the specification is great except one thing. This is the one thing. The specification says that begin can throw, yada yada, basically the same stuff, but here's one consequence of this specification is that a program can call begin only once, and subsequent calls to begin undefined behavior. So this is, I don't like this, how it is specified, because, for example, here we want to get one value from the generator and somehow modify it and yield. And if we are able to call begin only once, we'll have to write code a little bit different. So begin is not called more than once. And this means that after we call begin once, we can't use, for example, range 4, because range 4 calls begin again in this case, and calling in this case begin the second time is undefined behavior. So you can rewrite it kind of like this. We want to take one item from the generator. We want to yield a modified value from that generator, and after that we want to yield all the rest values from that generator. And in this case, we want to use 2 range 4 loops, but we can't do this according to this current specification, because the second range 4 loop will call begin second time, and this is undefined behavior. And this is what I don't like about how it is defined. So in case of STD generator, if you want to yield the whole generator, all the values of the generator, we need to use std ranges elements of wrapper to indicate for disambiguation purposes that we want to yield the generator. And in this case, it is not clear from the specification is this kind of code undefined behavior, because in the range 4 loop we call begin, but after that we don't call begin, but yield the whole generator using elements of. Is this undefined behavior? I don't know. It depends on the implementation, I guess. So again, once we call begin once, it renders usage and passing of this generator useless. Sorry for repeating the same words a lot of times, but in this example, passing a generator or moving the generator inside process values is kind of pointless, because inside you can only iterate over the values by calling begin, and we can't call begin, or rather by calling begin inside process values, we get undefined behavior, and kind of this is pointless. So probably it was modeled after iStream iterator, for example, in which case the constructor of the iterator changes the observable state, but it changes the observable state in a predictable manner. And moreover, I can restart or continue the iteration over the values that are stored inside my stream by constructing the iStream iterator again having the predictable side effects and change of observable state. And in case of begin, this is the only function that we can use to observe the state, and simultaneously this function changes the observable state. So when you call begin once, you changed the observable state, but you have no means to observe that state other than calling begin, in which case calling begin second time is undefined behavior. So I hope my blubbering makes kind of sense to you. So to summarize this, we can finally get, we will probably get standard generator type in C++ 23, which is kind of yay. The standard generator is recursive. It will have some reasonably small overhead to track nestedness. It's kind of whatever. And the part I don't like, mildly speaking, is that it is specified in a way that we can call begin only once. And this creates the problem of not being able to observe the changed observable state, or otherwise when you try to observe the observable state by calling begin the second time, you get undefined behavior. This is a bummer. So I hope they will fix it. And here is the last part that kind of makes the least sense, or it rather is the most difficult part of this talk. We have 15 minutes for it. So let's try to tackle it. So in the case of asynchronous generators, we switch gears a little bit, and we now have a notion of a result that will be ready at some point in time in the future. This result that will be ready in the future is represented by task. And you can co-wait on that task, for example, like here. And you can synchronously wait for that task that will be showed later. So here inside our asynchronous generator, we can not only suspend our coroutine when we yield the value, but we can suspend our coroutine when we co-wait for the result of some other asynchronous result. So in this case, we call get values async. We co-wait on the result, on the resulting task. At some point, this result will be ready. This coroutine will be resumed. We'll get our values, and we'll be able to, in this case, filter all the values with some kind of notion of validity, and will yield only valid values in this case. So this is how we can use our asynchronous generator. We can kind of try to shove the interface into for loop with iterators, but this feels kind of awkward because we can't just increment the iterator. We need to asynchronously wait for some kind of notion of the next value or next state, next iterator. And the consensus is that basically nobody does this, and everybody does it like this. We, in this case, have a while loop. We co-wait on the some notion of next element that we get from our generator. Co-wait expression results in optional like type that we can check for emptiness if this object is, if this result is empty, means that the generator has no more values. If this result is not empty, we can get the result, for example, by dereferencing this optional like type. In our case, we'll just use optional, not to complicate the things further. And let's see how we can do it. But first, here is an example of how we can get the result of this asynchronous the function that returns asynchronous result by synchronously waiting. In this case, as I mentioned in the first part, since we have lazy tasks, the whole kind of set of tasks will start executing when we call sync await. In this case, in this example, and in this particular case, we have no concurrency, and all the tasks and coroutines will execute synchronously on this thread, but asynchronous in the sense that at any time only one coroutine is resumed and other coroutines are suspended. You can imagine that if we have some concurrency, sync wait possibly blocks this thread, but anyway, we'll synchronously get the result of this whole asynchronous function call and store it in a variable value. So this is how it kind of works. We eventually get here in our coroutine. We have our generator initialized. We can call next, and we'll get next awaitable from that call on which we can co-await. And this coroutine may suspend or may not suspend if the result is ready. And let's consider, I'm sorry, in this case, in this particular case, when we co-await on the next, this coroutine will always suspend because we need to resume the No, I'm sorry, that is not right. So depending on the state of the generator, if the generator is suspended not at the point of co-yield, this point our coroutine can be suspended. And if our generator is suspended at co-yield, at the point of co-yield, this coroutine will be suspended. And I want to illustrate this case. So let's assume that nothing stops us from getting a value from our generator. And in this case, this coroutine will be always suspended, the coroutine in which we co-await for the next value from the generator. And continuation for our generator for G will be resumed. This continuation can be some other coroutine that our generator awaits on, or it may be the generator coroutine itself. Anyway, at this point, this coroutine, get paratest value coroutine, is suspended. We pass the control to the continuation of our generator. At some point, the control will get back to from our generator to this coroutine that is currently suspended. And at this point, this coroutine, the get paratest value coroutine, is resumed. The co-await expression results in an optional which may contain the result, the next value. I really hope this makes at least a little bit of sense, because this is really hard to grasp stuff. So yeah, this the control eventually gets back here. The coroutine is resumed. This coroutine is resumed. And we get the resulting optional to be stored in next variable. And so what lies ahead is separated by an even thinner veil from nonsense from this point on, if this weren't enough. And let's, we have 5 minutes. Let's try to go over this implementation really quick, just to be complete. So here's the overview of async generator type. We have promise type, we have move constructor, we have move assignment, we have destructor. These are very similar to what we had before. We have next call, next member function, which returns next awaitable, which is implemented inside promise type, initialized with current coroutine handle. And we have private constructor, which is used inside get return value inside promise. So this is the promise. We have get return object, initial spend, final spend. We have yield value functions, which in this case return yield awaitable instead of standard awaitable types. We have return void unhandled exception. We have our convenience facilities, get value, has exception, throw if exception. And finally, we have next awaitable. And in private section, we have our result variant, and we have continuation. So when we co-await on next awaitable, we co-await on this, an instance of this awaitable type. Constructor just stores the coroutine handle value. Await ready always tells that the result is not ready. At await suspend, we suspend the outside, this current coroutine that awaits on the next awaitable. We store that coroutine handle as continuation. So the coroutine that awaits, I will repeat it again, the coroutine that awaits on the next awaitable that we get from call to next is always suspended. it is stored as continuation inside our promise type, inside our generator, and the coroutine of the generator itself is resumed. So probably this is not entirely correct, but okay, let's pretend for a moment that this is correct. So await resume is the last part of the next awaitable. I'm sorry, I said about await suspend. Await resume is the last part in which we get the promise, get the reference to promise. We check if the coroutine is done. We throw exception if we had one, and return empty optional. Otherwise, if we have no exception. We otherwise, if the coroutine is not yet done, we return value that was stored inside our promise by moving it into the returning optional. So this is next awaitable type. The next things are get return object that returns an instance of our async generator. As initial suspend always tells that we need to suspend at the initial suspend point. We have a final suspend, which returns a final awaitable. We need to return this custom final awaitable because we need to, apart from telling to always suspend at final suspend point, we need to resume the continuation that we set by awaiting on next awaitable. So prior to this, continuation was set by waiting on the next awaitable. And at this point, when our generator is finishing execution, it has to resume that continuation. So basically, we have to get back to the coroutine that called that awaited on the async generator. So here we get reference to promise. We expect there to be a continuation, and we return the continuation coroutine handle using so-called symmetric transfer of control. And await resume in this case does nothing. Next is yield awaitable. Here we basically store either address of the object that we want to yield, or we store the copy of the value that we want to yield. And in both cases, we return yield awaitable. Yield awaitable looks like this. We want to always suspend when we co-yield some value. Await suspend is called when the coroutine, in this case, generator coroutine is suspended. Here we again use symmetric transfer of control, and to preserve correctness, we have to reset the continuation to null. This is the same continuation that was set by waiting on the next awaitable. And again, await resume does nothing. And this is kind of how it works. When we co-yield some value, it suspends this coroutine, the generator coroutine. The coroutine, the continuation that waited for the next value is resumed via symmetric transfer of control. And so the rest of the functions return void that does nothing, unhandled exception stores exception pointer. These functions basically the same. Get value gets reference to the stored result. has exceptions, checks for exception, throws exception, checks for exception, and rethrows exception if we have one. And next awaitable we already covered, and this is basically it. So again, this is the example. We have get value async that returns a task with some collection of values. We can then use it to, in our async generator, to co-wait on it, possibly suspending this generator coroutine. Eventually, we'll get back from whatever generated the values, and we can yield the values that we get asynchronously. And so the coroutine that uses this asynchronous generator can look like this. We create a synchronous generator. We loop over some kind of construction that is co-waiting on the next value, on the notion of the next value. If the co-wait can return an empty optional telling that the generator has no more values. It can return optional with a value, in which case we can use that value by dereferencing, access that value by dereferencing the optional. And otherwise, this co-wait expression can throw, indicating that an exception was thrown inside the generator coroutine. So here is the proper first part of this series of talks that I was telling about. You will be able to get the slides and all the references later, or by this link that you can see at the bottom of the screen. And at this point, we have no questions. Probably this nonsense scared all the people away. So I think that's it. Thank you, everyone who stayed up to this point, and bye-bye. See you next time.